Okay, so let us begin. We are looking at the A star algorithm, and if you remember what A star does is that it uses a function f n is equal to g n plus h of n, where g n is the known cost up to node n from the start node, because it has explored part of the space, and h n is the estimated cost from node n to the goal node essentially. So, it uses a combination of these two functions and basically picks node with lowest f of n at every point of time from the open list essentially. So, if you remember, g n was a function which we sort of inherited from branch and bound, which tries to keep it as close to the goal as possible, to the start as possible, and h n is a function we have inherited from best first search, which tries to pull it towards the goal node essentially. So, with a combination of these two functions, the idea is that the algorithm will find optimal paths to the from start to the goal essentially, and today we will show formally that this is how this is done. But before we do that, just a quick recap. Every time it generates a new node n, it gets different kinds of children, 3 different kinds of children. So, we had said, so when we say move gen, it gives new nodes, it gives nodes on open, and it gives nodes which are already on closed. So, when you generate, when you expand a new node, which means you call the move gen function with this node n, it can generate 3 different kinds of nodes. Either they are completely new, or they are already on open, or they are on closed essentially. So, completely new nodes are like this, and what we do is essentially compute the g values for these nodes, which is the g value of this node plus the cost of this arc essentially, and put it into open, and we mark a parent pointer from these nodes to this node n. So, these steps we do. For nodes which are on open and on closed, we need to revise g of m, where m is a child, because we might have found a cheaper path to the goal. So, for example, if this is a node on open, these two nodes are on open, then it is possible. So, since they are on open, it means that they already had some parent in the closed, of which it was a child. So, this could have been this one, this could have been this one. Remember that these double circles we will use for closed nodes. So, they already have some parent, but we have found a new path to these nodes on open. It is possible that we might have found a cheaper path, and we want to update the cheaper path. So, essentially we revise g values of nodes essentially. And lastly, you may get nodes which are on closed. So, for example, these two nodes, in which case not only you have to update the g values of those two nodes which are on closed, but also any nodes which might be pointing to this essentially. So, for example, if the cost, if the g value of this is let us say 50, and the edge, this edge is let us say 10, and if this g value was 70 for some reason, then we need to update that g value for that node, because now we have a cost of 50 plus 10 60. So, we want to make this 60, and we have gained a value amount of 10, which must be passed on to this. So, this must become minus 10, whatever its value was, it must become minus 10, and any children it might have and things like that. So, you need to propagate that value. Now, why do we need to do this updation open and closed list? Why do we bother to update these g values? In finding optimal solutions. or the shortest paths essentially. So, as and when, so let us take this example that we have been looking at. If this is a river and you are at this place which is a start node and your goal is somewhere here on the other side of the river. We have looked at this example before when you looking at best first search. So, you may generate some children and you may follow some path, because the heuristic function is driving it in this direction. But at that point you can see that there is the river on the way, and let us assume that the bridge is somewhere here or there is another bridge somewhere here, then the search will drive it towards that path essentially. So, it may go from here to here and then it may go from here to here. Now, best first search would have done the same thing, but it would have remembered this as the path which takes you to the goal node, and that is why we said that best first search does not guarantee you optimal paths. Whereas, so this is a path that you have just found for this node. This is a new parent that you have just found. It is possible that as search progresses you may generate a node here and you will find that the shorter path to this node is via here and not like this. So, this is the kind of situation we are trying to depict here, that you may want to revise, you may want to say this is not the parent, but this is the parent, and because there is a shorter path here. So, maybe you found a path like this. So, the path that you are looking for may be something like this, go like this, instead of the search would have generated first gone in this direction, because that is what the heuristic function is saying, the goal is here, go towards the goal, and then it will have veered away from that path essentially. What A star does is that when it does something like this, it reallocates parents to shorter paths to any node on the way. So, which is why we say that whenever we expand this node n, for nodes on open like these two or for children on closed like these two, if we have found a shorter path, we must update that essentially. And that is one reason why it ends up finding the shortest paths essentially. So, today we want to prove that A star is admissible and by this we mean that it will guarantee an optimal solution or shortest path. If you are trying to think of it as a path in a graph, the graph may be an abstraction for some other problem where the cost could be something else, but basically every edge has a cost associated with it. Okay. So, under what conditions will this algorithm, now just think of this purely as an algorithm, and what is the algorithm? The algorithm says that pick the node with the lowest f value from open, expand it, this is what we are doing here, and treat these three different kinds of nodes, new, open and closed, separately. For new nodes, just set up the graph. For nodes on open, check if you have found a cheaper path. For nodes on closed, also check whether you have found cheaper paths, but also propagate a cheaper path like in that example to the children of the closed node, because the node is unclosed, it will have some children. So, under what conditions would A star guarantee an optimal path? We have stated one condition earlier. So, let me write this here, conditions for optimality. The first condition is finite branching factor. Every node will have a finite number of children essentially. Now, obviously, you can imagine some continuous problems where there may be infinite neighbors. Now, if there are infinite neighbors, then we cannot use this algorithm. We will assume that every node has a finite number of children. So, the branching factor is finite essentially, that is one condition. We will allow infinite graphs, which means that we will allow for infinite number of nodes to be present in the graph, but branching factor cannot be infinite, which means that you can always move away from some node. If the branching factor was infinite, then you will spend all your time, infinite amount of time generating the children of that node essentially. So, obviously it will not work. There is a condition on the cost. So, we will use k for cost function. So, Kmn stands for cost of edge going from node m to node n. We will assume this is a symmetric cost. What condition should the cost function satisfy for the algorithm to guarantee optimal solutions? So, can I allow negative costs? Why? Sorry?
Loop.
So, if there is a cycle with some of its edges negative, then the algorithm will just keep repeating that cycle and its total cost will keep going down essentially, which is also a condition which Dijkstra's algorithm demands. Dijkstra's algorithm works only for positive cost. There are other algorithms which handle negative cost, but we are not looking at those kind of things. So, for the moment we will assume that this should be greater than 0, we will not even allow 0 costs essentially. So, that is for the moment, but we will come back to that a little bit later. A third condition that I have already mentioned and we have seen an example about it, which says that h of n should be less than or equal to h star of n, which means that the heuristic function must be an underestimating function. It must always underestimate the distance to the goal, never overestimate the distance to the goal. And the intuition behind that is, if you overestimate the distance of some node from the goal, then you will never explore that node further, because you will think it is too far from the goal. So, in general, if you think it is closer to the goal than it actually is, then you are likely to explore that node, and that is a key factor for A star being admissible. So, if you remember, we saw an example in which we saw two heuristic functions h1 and h2. One of them was underestimating the distance, the other was overestimating the distance, and both of them had a wrong notion of which of those two candidates was closer to the goal, but the underestimating function did find the optimal path and the other one did not. Today we will show this a little bit formally. So, if these three conditions are true, then A star is admissible, and by admissible we mean it always finds the optimal path. If there is a path from start to the goal, then it will find the optimal path from start to the goal and it will terminate with that. So, we will do this through a series of small lemmas. We will prove a series of statements and eventually conclude with this property of admissibility and a couple of more properties. We will compare heuristic functions to see if how can we say that one heuristic function is better than another heuristic function. So, we will have a series of lemmas. So, L1 simply says that it terminates for finite graphs. The algorithm will terminate for finite graphs. That is the only statement we want to assert at this moment. What is the justification or what is the reasoning to say that it will always terminate for finite graphs?
There are only fixed number of paths possible to be explored.
Yes, but that is not the justification that we are looking for. You should look at the algorithm. You should look at the algorithm and comment on what the algorithm is doing.
Each time we add a node to the closed.
So, if the graph is finite, then the algorithm in every cycle moves one node from open to closed. it starts by putting the start node on open list and close is empty, and in every cycle it inspects one node from open, the one which has the lowest F value, and if it is not the goal, it puts that into closed and generates its children and puts those children into open, which is a priority queue on F. So, if the number of nodes are finite in the graph, if the graph is finite, then this it can do this only a finite number of times. So, it will exhaust the whole graph. Now, supposing in this problem that we have here, which is this problem of the city travel, supposing these bridges were not there essentially, and there was a small hamlet here, which you could only explore that essentially. Then the graph, then A star would end up exploring all those nodes and say I have nothing else to explore because open has become empty. So, remember there are two conditions for exit. One is when open is empty, exit and report failure. Other condition is if the node that you have picked is a goal node, then reconstruct the path and return the path. So, in this case, if these bridges were not there and the goal was there, it would never find the path, but it would terminate. That is all we are talking about here essentially. So, the graph is finite, it will terminate. Then the second lemma we want to say is that at all times before termination, there exists a node, we will call this node n prime, and this node is on open and which is on the optimal path. So, I will just say an optimal path because there could be more than one optimal paths. So, the next statement that we are making is that before the algorithm terminates, it will always have in its open list one node which we will call n prime, which is on the optimal path from start to goal essentially. And the argument for that is the following, that initially we put S onto open. So, let us say this is optimal path, this is the optimal path, let us say there is only one optimal path to start with, n1, n2, n3 up to the goal. Let us say this is the optimal path. What we are claiming now, that from this path before the algorithm terminates, there would always be one node in the open list, which means the optimal path will always be in the sides of this algorithm in some sense. Now, when we start the algorithm, we put S onto open list. So, at the beginning S is in the open. If the algorithm is terminated by finding the path, then it is terminated, we are not talking of that condition, then it will pick the goal node essentially. So, we are talking about a condition before termination, which means there is a path to the goal, we are assuming there is a path to the goal, and it has not yet found a path or the path, whatever you want to say. We will show that when it finds a path, it always finds an optimal path. So, initially we put S onto open. So, the condition is true in the initial situation. When we remove S from open, we put it into closed, and then we end up putting n1 onto open essentially. If you remove n1 from open, then we put this into closed and we will end up adding n2 onto open, and this process will continue essentially. If we remove G from open, which is the last in this line, that means the algorithm is terminated by finding a path essentially. So, this condition says that at any time one of these nodes is always in the open, which is available to A star to inspect next. Further, we say the F value of this node is always less than or equal to the optimal cost from. So, S is a start node and remember F star is the optimal cost of going from start to the goal node essentially. So, this is part of the statement. We are saying that not only does such a node exist, it will always have F value which is lower than or equal to the optimal cost. So, what is the argument behind this? You can say that f of n prime is equal to g of n prime plus h of n prime, that is by definition of what the f value is. Now, because it is on an optimal path, we know that this is g star of n prime plus h of n prime. Remember, we are talking of nodes on this optimal path. This will be less than equal to g star of n prime plus h star of n prime, because of the condition number 3, which we have said that the heuristic value is always less than or equal to the optimal value, which means this is equal to less than or equal to f star of n prime, where f star of n prime is the cost of the optimal path which passes through n prime. So, not necessarily the globally optimal path, but the optimal path which passes through n prime. But this n prime that we have chosen is on the optimal path itself. So, this must be equal to f star of s, because after all it is the same path that we are talking about. So, whether we say it is a passing through n prime or so, whether we say it is passing through s or n 1 or n 2 or n 3 or g, it does not matter, the cost is still the same. So, this is a condition that we are looking for, that this is less than or equal to this f star of s prime, that is what we have written here. Okay. Then the third thing we want to say is that algorithm terminates if there is a path and I should add even for infinite graphs. Remember that an infinite graph can only be that which has an infinite number of nodes, but with branching constant branching factor. So, the third statement we are making is that the algorithm terminates with a path that if there is a path from the start to the goal state, the algorithm will always terminate with a path from the start to the goal state. We are not yet talked about optimal path, we are saying that it will find a path, and we are saying, making this claim that even if the graph is infinite, even if there are an infinite number of nodes, then the algorithm will find a path to the goal node. What would be an argument for this? In other words, we are saying that the algorithm will terminate by picking the goal node. Of the two termination criteria that we have, one is the open is empty. In this, for infinite graphs, open can never be empty. So, for infinite graphs, it can only terminate by picking a goal node essentially. So, we are saying we want to argue that it will necessarily pick the goal node at some point of time. Just you have to imagine this graph, just imagine it doing a search in a city or something like that. How the open frontier will move essentially. So, remember that it always picks the node with the lowest f value essentially. For a goal node, the f value is equal to the g value of that node, because h is 0, you are already at the goal. So, we want to argue that this node with the goal, which is the goal node, will at some point come to the head of this sorted list or at the root of the heap if it is a way of maintaining a priority queue. In other words, we are saying that all other nodes on open will at some point become more expensive than this node G. And why is that? No, not due to HN. So, what am I saying? I am saying that let us say this is my start node and this is my path to the goal. It has some cost essentially. What I am saying is that this search cannot ignore this goal node, that eventually it may end up looking at a node here, it may end up looking at a node there in this direction or that direction, but it cannot go indefinitely in any direction. And the reason for that is that whichever direction it goes, the G values, think of the G values, supposing there is a node here, let us call it N1 or something, if that is on the open list. So, let us say the open is looking something like this, refusing to go towards the goal node, but there is a node N1 on G value. What is going to be this G value of this node? It is going to be the length of the path from here to here. Let us say it picks this node N1, it will have some other node, let us call it N2, and then it let us say picks N3. Can it keep doing, can it keep going indefinitely along some other direction? Because the G value, because the paths are becoming longer and longer in this other direction. G value, remember, is the length of the path found up to that point, and at some point this f value will become the smallest. That is a condition that we have, that the paths are edges are positive in cost essentially. So, if you try to go in some direction, at some point your cost will become. So, what is the value of this? Some G of G is some value. At some point all other nodes that you have in open will have paths which are longer than this, or to think of it in another manner, there are only a finite number of paths which are shorter than this length G of G, and even if the algorithm will explore all those paths and then it will pick up G of G. Is this okay, or there seems to be a deathly silence about this? So, all we are saying is that if you go off in some other direction, your path cost will become more than the cost of this G value, and remember that the heuristic function underestimates. So, you can never overestimate the cost to, so that in any case G will come at some point, and at some point this will become the smaller. So, it will have to pick the node. Okay. So, as it turns out, this was many years ago when I was teaching the same very point in the class. One of the students in the class, he is now a professor in Princeton, raised his hand and said this is not correct, and it is something to do with this condition. That is why I said for the moment let us assume this condition is the paths, the edge of E, the cost of each edge is greater than 0. So, it is possible to assign edges, edge costs. For example, I will assign 1 to the first edge, half to the second edge, 1/4 to the third edge, 1/8 to the fourth edge, and keep dividing by 2. What will happen? I will have an infinite path whose total path length will be finite essentially, and that finite could be less than this G value, which means that it could get actually trapped in that infinite path, which has a finite total cost. So, this is like that paradox is that the rabbit and the hare paradox, that Epidemics paradox, that you say that the rabbit, the tortoise tells the rabbit that if you give me a lead of let us say 100 meters, then you can never beat me in a race. And his argument is the following. So, let us say rabbit is at a starting point and the tortoise is 100 meters away. The tortoise say that by the time you come to this 100 meters point, I would have moved to some point, let us call it x1 essentially. Then by the time you come to x1, I would have moved to x2, and by the time you come to x2, I would have moved to x3, and this will of course keep happening infinitely, and so you can never overtake me essentially. So, this is one of those paradoxes which comes into the picture, and something similar would happen if we were to allow arbitrarily small edge costs essentially. So, if we cannot allow arbitrarily small edge costs, then this would not happen. So, which is why the correct condition is not greater than 0, but greater than some value epsilon, some positive value epsilon, and as long as that is the case, it cannot be infinitesimally small, then every path will at some point become longer than this path to G, and then G will come into contention. So, I will take it that this point has been accepted. Okay, so, what have we done so far? So far we have said between statements 1 and 3, 1 we said that the algorithm will always terminate. In 3 we said if there is a path to the goal, it will always find a path to the goal. Now we are saying that it will always find the optimal path to the goal, and it has a very simple argument. The argument is as follows, that so the proof for this I will write here. Let A star terminate with a non optimal path, which means it has found some path to the goal where the G value of that path. So, let me just call it G1 is greater than f star of S. Remember, f star of S is the optimal path. Whenever we use the star, it is an optimal path, whether we know the value or not essentially. So, we are saying that let, so we are doing proof by contradiction in some sense. Let A star terminate with by picking a goal node G1 whose G value is more than the optimal cost. And now I want to make a statement that this cannot happen. So, let me ask you, why can this not happen? Why can it not terminate by finding a non optimal path? So, if it has picked the goal node, it will terminate, that is the algorithm that you must remember, like the branch and bound algorithm. If it picks the goal node from open, that means it will terminate, it will say I found the goal, reconstruct the path and so on. Now, we are saying that let it terminate by picking the goal node G1 such that its cost is more than the optimal cost. Remember, f star of S is equal to f star of G, and in fact, it is f star of any value on this node essentially. All of them, the values are the same, it is a cost of the optimal, it is a cost of this optimal path. So, we are saying that assume that A star terminates by picking a value which is more than the optimal cost. Now, what I am trying to say is that we cannot make this assumption. I mean, it is not a long proof or something, it is just one statement which says that it can never pick this such a node and terminate. So, you have to look at the statement number 2 that we have written here. There is a reason for every statement. That statement says that at all points before termination, there exists a node n prime which is on the optimal path and whose f value is less than f star of S. So, simple answer is it cannot. Why? Because it would pick n prime, as simple as that is. The algorithm simply says pick the one with the lowest f value. So, just imagine that it is about to terminate by picking this goal G1, and this goal G1 has its cost more than F. So, it will never be at the head of the priority queue essentially, because we have said that at all points before termination there is always a node n prime which is on the optimal path and which is on open. So, if this n prime is on open and its value is less than f star s. So, it has if A star has to choose between these two nodes, one whose value is less than or equal to f star s and one whose value is definitely greater than f star s. Remember, I have written g of g, I could have written f of g, it is the same thing, because f of g is equal to g of g plus 0, because h is 0. So, you can write f of g or g of g, it does not matter, it is the same thing. So, if A star had to pick between these two nodes n prime and g 1, it would pick n prime, which means it cannot terminate by picking g 1 like this. So, the only time it can pick a goal node is that if it is at least as good as the optimal cost node. So, it will always terminate only with an optimal path. Is that okay? So, now we want to look at one more property, and this is as for okay. So, one more statement before that property that I am talking about is that for every node n that A star picks, f of n is always less than or equal to the optimal cost. So, we are saying that A star will only pick nodes whose f value is less than the optimal. All this is stemming from the fact that the heuristic function is underestimating, because the heuristic function underestimates, we have shown that nodes like this will always be less than optimal cost, or there will always be such a node with less than optimal cost. And now we are saying the same argument as we did for this case 4, that if A star is going to pick this node n, it must be better than n prime, because it has picked n, and if it is better than n prime, it must be less than or equal to f star of s. So, it will only pick nodes which are better than or equal to the optimal cost nodes. L6 is a question that I am interested in. So, let there be two functions. So, we say H2 is more informed than H1 if for all nodes H2 n is greater than H1 n. So, if the heuristic value H2 is greater than H1 n, then we say that H2 is more informed. Just a definition. We say then if this is the case, then every node seen by A2, and A2 is one version of A star which is using this H2 function, is also seen by A1 star. So, let us say we have these two versions of A star algorithm, one uses this H2 function heuristic function, the other uses the H1 heuristic function, and H2 is always greater than H1 of n. We say that H2 is more informed than n. So, take the extreme case when H1 is equal to 0. If H1 is equal to 0, it always thinks that the cost to goal is 0 essentially, which is what branch and bound does, whereas H2 thinks that it is at least some value. So, such a function is called more informed, and we are making a claim that if H2 is more informed than H1. So, I should write if here, if H2 is more informed than H1, then every node seen by A2 star is also seen by A1 star, which means A2 star will see in general a smaller number of nodes, or which means it will explore a smaller part of the search space essentially. It will be more focused towards the search. So, we will do this proof by induction. and you can see that for the start node this property is true. So, what is the property we are trying to prove? That if A1, if A2 sees some node, then A1 also sees that node. We want to prove that. So, let us call this property P, that if A2 sees a node, A2 star, why star? Because both are admissible. So, what is the situation? Situation is like this, that for any given node n, there is a band starting from 0 to h star of n. What we are saying is that h2 is somewhere here and h1 is somewhere here. This is what we mean by more informed, it is closer to h, the optimal value. And we want to make a claim that if this is the situation, then the search space explored by the algorithm using h2 will be smaller than the search space explored by algorithm using h1. And we will do this proof by induction. So, you can see that for S, so we will call this statement P. So, P is true for S, which is a start node. So, we are just saying that if A1 sees, if A2 sees the start node, then A1 will also see the start node, which is trivially true, because both the algorithms or the A star always starts by picking the start node essentially. So, the second part is a hypothesis which says that let, so I will just use this for this whole statement. So, instead of every, let me say any node, which is the same thing essentially. So, let P be true for depth k1 or depth k. Now, we want to show that this is also true for depth k plus 1, which is the induction step, and this we will do by contradiction. So, let n be a node at depth k plus 1, which is picked by A2 star, and let A1 star terminate without picking n. So, the induction step we will do by contradiction. So, we are making an assumption that there is some node, we have called this capital N at depth k plus 1, and we are saying A2 star has picked that node, but A1 star terminated without ever picking that node essentially, which means A1 star found a path to the goal. Now, if you look at this value f2 of n, so f2 is for the second algorithm which is using h2, is g2 of n plus h2 of n. So, we can rewrite this as h2 of n and this is less than f star of s. Remember that every node that you pick, the statement 5 that we made will have its value less than f star of s. So, we are just writing f star, it does not matter f1 or f2, it is the optimal cost, f star s starts for the optimal cost. So, we can write this as h2 of n is less than or equal to f star of s minus g2 of n. Now, A1 star has terminated without picking this node n, which means that f 1 of n is greater than or equal to f star of s. It cannot be less than f star of s, because a 1 star has terminated, and it will terminate by picking a node with the optimal cost value, and it has not picked n. So, this inequality must hold, that it must be at best equal to that, but it cannot be less than that essentially. So, this we can rewrite as the following: f star of s is less than or equal to g 1 of n plus h 1 of n. I am just rewriting this. I am replacing f 1 of n by g 1 of n plus h 1 of n, and I have just inverted the sign, inequality sign essentially. Now, the question I want to ask is, what is the relation between g 1 of n and g 2 of n? This g 1, this g 2 of n and g 1 of n. If I were to put an inequality, what would I put, or equal to? What is the relation between this? What should I put? What symbol should I put in between here? G 2 is greater than or equal to. You are the only one who is saying that. Why is it? Why is it the case?
Because G1 of n, like A1 needn't have found the optimal.
Neither of them need be optimal. They are only the paths found so far.
Path found so far by A2 need not be the optimal, like path to n.
Okay, you are close to it. You are not getting there exactly, but you must remember this statement we made. Let this condition be true up to depth k, the induction hypothesis, which means that every node that has been seen by A2 up to depth k has also been seen by A1. So, whichever path A2 found, A1 would have also seen that path, but maybe it had seen some other path as well. So, this will be greater than. So, it is possible that A1 might find a shorter path to n, because it has explored more nodes on the way to n essentially. In the it could always be equal, but we are saying it does not have to be equal. So, the point of this whole exercise is that we can replace this by g 2 of n. Okay. We can rewrite this as okay, we can replace it by g 2 of n plus h 1 of n, which means we can write this as f star of s minus g 2 of n is less than or equal to h 1 of n. So, okay, I just brought g 2 onto the left hand side and rewritten this statement here. So, I have this f star of s minus g 2 of n is less than or equal to h 1 of n. N is that node which A1 did not pick, and that is why we could write this inequality. Here we have said the same thing, that this is less than this, and therefore, simply by transitivity here, h 2 of n is less than or equal to h 1 of n, which is a contradiction, because we assumed this, that h 2 of n is always greater than h 1 of n, and here we have said that if this, and this is only assumption we have made, that let A1 star terminate without picking n, and that has led to this statement which contradicts our original statement essentially. So, this cannot be the case, and therefore, it cannot terminate without picking n, which means that if A2 has picked this node n, A1 also must pick this node n, and which is the statement we are making, that every node seen by A2 will also be seen by A1. So, the effect of this is that the space explored by A2 is contained, not necessarily strictly contained, but contained in the space explored by A1 essentially. So, it always pays to have a better heuristic function. The higher the H1, H2, the better it is for us. Any questions here? So, there is one more property which needs to be looked at, but we will do that in the next class. So, I will stop here and we will sort of come back to this A star and its behavior. We will do a quick recap in the next class and then we will start again. Okay. So, I will stop here.